Look up at the night sky. What do you see? A breathtaking tapestry of stars, galaxies, and cosmic wonders, all arranged in what seems like perfect order. But rewind the clock, go back far enough, 13.8 billion years, and you would find something almost incomprehensible. A universe not of light and structure, but of searing heat, blinding energy, and what appears to be pure, undiluted chaos. How did we get from there to here? How did our beautifully complex and ordered universe emerge from what scientists call the primordial chaos? It's a question that has captivated thinkers for centuries, a mystery that taps into the very origins of everything we know. And today, we're setting out on a journey to explore exactly that, from the first unimaginable moments of existence to the vast, structured cosmos we call home. This story isn't just about science, it's about one of the greatest transformations in the history of reality. Imagine a beginning so turbulent that matter and energy were indistinguishable, where the laws of physics as we know them hadn't yet settled into place. In those first instants, the universe was a roiling sea of potential, a place where randomness seemed to rule. Yet, hidden within that chaos were the seeds of everything to come: galaxies, stars, planets, and life itself. We'll trace how subtle symmetries broke, how forces separated, and how the faintest ripples in the fabric of space-time grew into the cosmic architecture we admire today. It's a tale of emergence on the grandest scale, and it invites us to rethink what order and chaos truly mean. You're about to embark on an adventure through cosmic history, one that spans from a single point of infinite density to the sprawling universe we inhabit now. We'll explore how quantum fluctuations shaped galaxies, how dark matter sculpted the cosmos, and how the laws of nature conspired to turn chaos into complexity. This isn't just a story of the past, it's a window into our own place in the universe, a reminder that we are products of that ancient transformation. So settle in, open your mind, and get ready to witness how order arose from the void and how our universe found its way out of chaos. When we talk about the early universe as a state of chaos, we are not simply using poetic language. In cosmology, chaos has a very specific scientific meaning rooted in the laws of physics. It describes a condition of extremely high entropy. Now, entropy is often thought of as disorder or randomness, a measure of how disorganized a system is. In those first fleeting moments after the Big Bang, the universe was packed with an unimaginable density of energy, a searing hot soup where the fundamental forces we know today, gravity, electromagnetism, and the nuclear forces, were fused into one. Particles and antiparticles flickered in and out of existence, colliding and annihilating in a frenzied dance. There was no structure, no stable matter, no clear distinction between one thing and another. It was the ultimate high-entropy state, a formless, energetic blur where randomness truly reigned supreme. This stands in the starkest possible contrast to the universe we see when we look through a telescope today. We observe breathtakingly ordered spiral galaxies, elegant solar systems with planets orbiting in precise, predictable paths, and intricate physical laws that operate with mathematical consistency. A star ignites and burns for billions of years in a stable, sustained reaction. This is a universe of remarkably low entropy in many of its localized structures. So how did we get from that initial, uniform fog of energy to this cosmos of complex, organized islands? The journey from cosmic chaos to order isn't a violation of the laws of thermodynamics, which state that the total entropy of the universe always increases. Instead, it's a story of how that overall increase in entropy actually drove the formation of local pockets of exquisite order. Think of it this way. Imagine a freshly poured cup of coffee with a dollop of cream on top. Initially, the cream and coffee are separate, a state of lower entropy. As you stir it, they mix into a uniform, tan-colored liquid, a state of higher entropy and greater disorder. This is the inevitable direction of the universe, but now picture that process in reverse. Our universe did something even more astonishing. It took that initial, perfectly mixed, high-entropy state, the hot, dense soup, and as it expanded and cooled, it somehow managed to create separated structures. Galaxies are like the cream slowly gathering back together, not in defiance of the overall trend, but because the relentless drive toward greater overall disorder created the conditions for local complexity to emerge. The expansion of the universe provided the energy and the canvas, and the subtle imperfections in that primordial chaos became the seeds from which all structure would grow. But to truly understand the nature of that primordial chaos, we must venture even further back to a time that pushes the very limits of physics and philosophy, the moment of the Big Bang itself, and the tantalizing question of what, if anything, came before it. Our entire story of cosmic emergence hinges on that initial spark, yet its origin remains perhaps the greatest mystery in all of science. The equations of general relativity that so elegantly describe the expanding universe break down completely at time zero, at a point of infinite density and temperature known as a singularity. It's as if the cosmic record of existence has its first page ripped out, leaving us to wonder about the prologue. One compelling line of thought suggests there was no before in any conventional sense. The Big Bang may not have been an explosion in space and time, but rather the very origin of space and time itself. In this view, asking what came before the Big Bang is like asking what is north of the North Pole. The question itself may be a grammatical trap, born from our innate need for a linear narrative with a clear beginning, middle, and end. The universe might simply have begun with the concepts of before and after crystallizing into existence along with the first moments of reality. Yet, physicists are naturally reluctant to accept a true nothing as an explanation. This has given rise to several profound theories that attempt to peer beyond the veil. One of the most prominent is the idea of a quantum fluctuation. In the strange world of quantum mechanics, empty space is never truly empty. It's a seething foam of virtual particles that spontaneously pop into and out of existence, borrowing energy from the vacuum for fleeting instants. Perhaps our entire universe is the ultimate quantum fluctuation, springing from a pre-existing, timeless quantum field. From this perspective, the Big Bang wasn't a singular event but a transition, a bubble of space-time nucleating and then rapidly inflating into everything we see. This concept dovetails with the mesmerizing, if speculative, idea of a multiverse. If eternal inflation is correct, our Big Bang may not be unique. Instead, we might inhabit one bubble in a vast cosmic froth, a single universe in an infinite multiverse where the laws of physics are different in each domain. In this grand tapestry, what we call the Big Bang is merely our local beginning, with an endless expanse of other universes, each with its own story, stretching into an unfathomable past and future. Other theories reach even further. The cyclic model proposes a universe with no beginning or end, but an endless cycle of expansion, contraction, and rebirth. In this view, a previous universe may have collapsed in a big crunch, rebounding into our own Big Bang in an infinite cosmic cycle. Then there is the concept of the cosmic egg, a notion that predates modern cosmology, a single, timeless, infinitely dense state containing all potentiality that somehow fractured, giving birth to the dimensions and forces we know. What all these theories share is a common thread linking back to our emergence from chaos. They suggest that our universe's origin, however it occurred, was not a perfectly ordered, pristine event. It was likely messy, probabilistic, and rooted in a deeper, perhaps quantum, form of randomness. The initial conditions were set by processes we do not yet understand, processes that may forever lie beyond our observational horizon. This foundational uncertainty, this ultimate unknown, is the deepest wellspring of the chaos from which our ordered cosmos somehow crystallized. It means the seeds of galaxies, stars, and life itself were sown in a realm of physics that remains just out of reach, making our existence not just a miracle but a profound mystery. To grasp the true depths of the primordial chaos, we must journey to the very edge of scientific understanding, to a time so brief it defies imagination. We are venturing into the Planck Epoch, the first 10 to the power of -43 seconds of our universe's existence. This is not merely an early chapter in our story. It is the foundational moment where the very concepts of space and time as we know them begin to fray. At this scale, the universe was compressed into a space a billion times smaller than a single proton, with temperatures soaring to inconceivable heights. In this environment, the energy densities were so extreme that the two great pillars of modern physics, Einstein's theory of general relativity, which governs the very large, and quantum mechanics, which governs the very small, completely break down. Their equations produce nonsensical answers, infinities that signal our models are utterly insufficient. This era represents the ultimate chaos because it is a realm where the rulebook for reality had not yet been written. During this fleeting instant, the four fundamental forces that orchestrate our universe, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were not separate entities. They were fused into a single, unified superforce. In our present day, these forces operate with distinct strengths and over different ranges, governing everything from the orbit of planets to the binding of atomic nuclei. But in the searing heat of the Planck Epoch, the energy was so intense that it overwhelmed the differences between them, forcing them into a state of perfect symmetry. There was no matter as we recognize it, no particles, not even a clear distinction between energy and the fabric of spacetime itself. The universe was a swirling, chaotic foam of pure potential, where the geometry of spacetime itself was subject to violent, random fluctuations. This was a reality where cause and effect, location and duration had no stable meaning, setting the stage for everything to come. This chaotic foundation was not a blank slate but a dynamic, probabilistic arena where the first seeds of our structured cosmos were unknowingly planted. The extreme conditions of the Planck Epoch are believed to have generated the primordial quantum fluctuations that would later become the blueprint for the entire universe. Imagine the fabric of spacetime at this time not as a smooth sheet, but as a turbulent, bubbling ocean. Within that foam, microscopic ripples were constantly forming and dissolving due to the inherent uncertainty of quantum mechanics. These ripples were the first faint imprints of structure, tiny variations in density that were frozen into place by the event that immediately followed, cosmic inflation. Without the chaotic quantum gravitational turmoil of the Planck Epoch, there would have been no seeds for gravity to amplify. There would be no galaxies, no stars, no planets, just a perfectly smooth, empty, and forever featureless void. While a complete theory of quantum gravity remains the holy grail of modern physics, attempts like string theory and loop quantum gravity offer tantalizing glimpses into what might have occurred during this mysterious era. They suggest a reality where spacetime itself might be quantized, composed of tiny, indivisible units much like pixels on a screen. In this view, the chaos of the Planck Epoch might have been a frenetic dance of these fundamental spacetime building blocks. It is a profound thought that the very order we see today, the majestic spiral of a galaxy, the precise orbit of a planet, owes its existence to the random, unpredictable, and ultimately chaotic processes that occurred when the universe was at its smallest and most volatile. The Planck Epoch is the ultimate origin story, a reminder that our entire cosmic existence hinges on a moment of beautiful, terrifying chaos where physics as we know it began. Out of that initial, unfathomable chaos of the Planck Epoch, our universe needed a mechanism to transform its raw, quantum potential into something tangible. It needed an event of such staggering power and precision that it could take those microscopic ripples and stretch them across the cosmos, effectively writing the first draft of cosmic history. That event is known as cosmic inflation, and it stands as one of the most pivotal and elegant ideas in all of cosmology. Think of it as the universe's ultimate growth spurt, a period of exponential expansion that took a region of space smaller than a subatomic particle and blew it up to the size of a grapefruit in a mere fraction of a second. This wasn't a gentle unfolding, it was a violent, explosive stretching of the very fabric of spacetime itself. The driving force behind this incredible expansion is thought to be a mysterious energy field called the inflaton field. Picture this field as a kind of cosmic engine, saturating all of space and pushing it apart with an immense negative pressure. For that brief instant, this field dominated the universe, and its repulsive gravity caused space to expand faster than the speed of light. It's a concept that seems to defy Einstein's rule that nothing can travel faster than light, but crucially, it is spacetime itself that is expanding. The objects within that space aren't breaking any speed limits. This period of inflation solved several major puzzles in one elegant sweep. It explains why the universe appears so remarkably flat and uniform in all directions, because inflation stretched a tiny, homogenized patch to become our entire observable universe. It also explains why we don't find any exotic relics like magnetic monopoles. They were simply diluted away to nothingness by the incredible expansion. But perhaps inflation's most profound gift was its ability to create order from randomness. Remember those quantum fluctuations from the Planck Epoch? Those tiny, random ripples in the fabric of spacetime. Inflation acted like a cosmic projector, taking those infinitesimally small imprints and magnifying them to an astronomical scale. As space expanded exponentially, it froze these quantum jitters into permanent, classical variations in density. Areas that were slightly denser than average due to a random fluctuation became the seeds for future gravity to work upon. This is how randomness was forged into structure. The universe didn't start with a blueprint for galaxies. It started with a random roll of the quantum dice, and inflation ensured that those dice would determine the fate of the entire cosmos. Without this process, our universe would be a very different and far emptier place. Without those amplified density variations, gravity would have had nothing to grip onto. Matter would have been distributed with near-perfect uniformity, and the force of gravity would have been too weak everywhere to pull anything together. There would be no clumping, no collapse, no galaxies or stars, just a vast, ever-cooling sea of thinly spread particles. Inflation provided the initial conditions that made our structured universe not just possible but inevitable. It turned the faintest whisper of quantum noise into the gravitational melody that would orchestrate the formation of everything we see. The evidence supporting this incredible theory is etched across the sky. The cosmic microwave background radiation, the afterglow of the Big Bang, is not perfectly smooth. It contains tiny temperature variations on the order of 1 part in 100,000 that form a specific pattern exactly predicted by inflationary models. These minute hot and cold spots are the direct imprint of those primordial density fluctuations, the blueprint from which all cosmic structure grew. It is a stunning confirmation that our vast and complex universe owes its existence to quantum mechanics operating on a microscopic scale, amplified to cosmic proportions by a brief but epoch-defining event. Inflation was the great organizer, the moment the universe took its chaotic quantum origins and began writing them large across the heavens, setting the stage for the next great act, the creation of the first elements. With the stage set by the explosive expansion of inflation, the universe entered its next critical phase, a period of profound transformation where the very rules of physics were being written. As this rapidly expanding cosmos continued to cool, it crossed energy thresholds that would forever change its character. The first and most crucial step in moving from a formless sea of energy to a structured universe was the differentiation of the fundamental forces. In that initial, unimaginable heat, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were not distinct entities but were unified into a single, symmetrical superforce. There was no distinction between the force that binds atoms and the force that guides planets. They were one and the same, a perfect but featureless symmetry. This state could not last. As the universe expanded and its temperature plummeted, it underwent a series of spontaneous symmetry breaks. Think of it like water cooling. Steam, a chaotic gas, has a high degree of symmetry. It looks the same in every direction. As it cools and condenses into liquid water, that symmetry is broken. The water now has a distinct surface and volume. If it cools further into ice, its molecules lock into a rigid, crystalline structure, breaking symmetry even further and creating a new, more complex order. In a very similar way, the cooling universe underwent phase transitions. As it crossed certain critical energy thresholds, the unified superforce could no longer maintain its perfect symmetry. It fractured, or more accurately, it crystallized into the distinct forces we recognize today. The first force to peel away was gravity. This makes intuitive sense, as gravity is by far the weakest of the four forces, albeit with an infinite range. Its separation marked the first step in creating a rulebook for the cosmos, providing the overarching framework that would eventually shape the largest structures in existence. Next, the strong nuclear force split off. This is the immensely powerful glue that binds quarks together to form protons and neutrons, and later holds atomic nuclei together against the tremendous repulsive force of positively charged protons. Its emergence was absolutely vital. Without the strong force, no complex atomic nuclei could ever exist, and the universe would forever be a soup of free quarks and leptons. Finally, the electroweak force separated into the two distinct forces we now call electromagnetism and the weak nuclear force. Electromagnetism governs the world of light, chemistry, and biology. It's the force responsible for holding atoms together into molecules and allowing your eyes to see this screen. The weak nuclear force, while less familiar, plays a specialized and crucial role in nuclear processes like radioactive decay and the nuclear fusion that powers the sun. This final separation effectively completed the cosmic toolkit. The universe was no longer a place of unified, undifferentiated energy. It now had a set of distinct laws, a physics rulebook with 4 fundamental chapters, each with its own strength, range, and purpose. This differentiation did not just create abstract rules, it actively sculpted the chaos into the first hints of structure. The forces began to govern the behavior of the primordial particles that were now able to condense out of the energy soup. Quarks, freed from their previous state of asymptotic freedom, could now be captured and permanently bound by the strong force into protons and neutrons. Electromagnetism began to dictate how charged particles would interact, attracting and repelling. This establishment of the forces was the essential prerequisite for everything that followed. It turned a chaotic, lawless arena into a cosmos governed by predictable mathematical principles. The randomness of the quantum fluctuations was now subject to a strict and reliable set of commands, allowing gravity to amplify the dense regions into galaxies and allowing nuclear forces to forge the first elements. The universe had moved from pure potential to a system with rules, and those rules would now guide its evolution for billions of years to come. With the fundamental forces now distinct and operating under their own unique laws, the universe possessed the rulebook necessary to build something tangible. But it still lacked the physical building blocks. It was an arena of immense energy, but to construct galaxies, stars, and planets, that energy needed to condense into stable matter. This transformation, the genesis of the very first particles from pure energy, is one of the most astounding processes in cosmic history. As the universe continued to expand and cool, it eventually reached temperatures low enough, though still in the trillions of degrees, that the frenetic dance of energy could coalesce into the first specks of solid reality. This process is a direct consequence of Einstein's most famous equation, E equals mc squared. We often think of it as describing how matter can be converted into a tremendous amount of energy, as in a nuclear bomb. But the equation works both ways. Under the right conditions of extreme heat and density, energy can spontaneously transform into matter. In the early universe, this happened continuously. The cosmos was so packed with radiant energy that pairs of particles and their opposite counterparts, antiparticles, were constantly bursting into existence. Photons of light would collide and spontaneously create a matched pair, perhaps an electron and its antimatter twin, the positron. These pairs would then almost immediately meet another counterpart and annihilate each other, converting right back into pure energy in a flash of light. For a brief period, this was the dominant cycle of existence, a restless, shimmering sea of creation and destruction where matter was a fleeting phenomenon. As the cosmos cooled further, this endless cycle began to break down. The energy of the photon collisions dropped below the threshold needed to create new particle-antiparticle pairs. The annihilations continued, but the creation stopped. In a perfectly symmetrical universe, this would have been the end of the story. Every single particle of matter would have found an antiparticle, annihilated, and returned to energy. The universe would have been left with a sea of light and nothing else, no atoms, no chemistry, no possibility for life. Yet that is clearly not what happened. We live in a universe made almost entirely of matter. Our bodies, our planet, the stars we see at night, they are all constructed from protons, neutrons, and electrons. For our material existence to be possible, a profound and mysterious asymmetry must have occurred in those first moments. This is the great puzzle of baryogenesis, or the creation of matter. For some reason, there was a tiny 1 in a billion imbalance in the amounts of matter and antimatter produced. For every billion antiprotons created, there were 1,000,000,001 protons. For every billion positrons, 1,000,000,001 electrons. This minuscule excess, a mere fraction of a percent, was our universe's saving grace. When the great annihilation finally concluded, all the antimatter was gone, along with an almost equal amount of matter. But that tiny surplus of matter, that one extra particle in every billion, was left behind. It is from this incredibly slim margin that every galaxy, star, and planet was formed. We are the remnants of that ancient, inexplicable imbalance. The question of why this asymmetry exists remains one of the biggest unsolved problems in physics. The standard model of particle physics does contain the necessary conditions for creating such an imbalance, a principle known as CP violation, but its measured effect is far too small to account for the vast amount of matter we see in the universe today. This suggests that the answer lies in new physics beyond our current understanding, perhaps in the behavior of ultra-rare particles like neutrinos in the early universe, or in processes that occurred during the grand unification epoch before the forces separated. Whatever the cause, this break in symmetry was the pivotal event that allowed a material cosmos to emerge from the energy of the Big Bang. It turned a universe that was destined to be a featureless void of light into one brimming with the potential for complex structure. The particles that survived that great annihilation, the quarks, electrons, and neutrinos, were now free to begin the next, even more complex stage of construction, building the first atomic nuclei. Armed with the first stable particles and governed by a complete set of physical laws, the universe was poised for its next great creative act. For a brief, spectacular window of time, the entire cosmos functioned as a colossal nuclear furnace, forging the raw ingredients for everything that would ever exist. This era, known as Big Bang nucleosynthesis, represents the universe's first successful attempt at building something more complex than elementary particles. It's the moment we transition from a plasma of quarks and photons to a universe containing the first atomic nuclei, the primordial seeds of all future chemistry, and indeed of life itself. The stage for this event was set by the continuing expansion and cooling. Within the first 3 minutes, the temperature had dropped from trillions of degrees to around 1 billion degrees. This was still impossibly hot by any human standard, but it was finally cool enough for protons and neutrons to exist as stable individuals, no longer at risk of being blasted apart by high-energy photons. These particles were now like bricks scattered across a construction site, ready to be assembled. But the force that could bind them together, the strong nuclear force, had to overcome a major obstacle: the intense electromagnetic repulsion between positively charged protons. To fuse, they needed to be slammed together with tremendous force. This is where the conditions of the early universe provided the perfect environment. The entire cosmos was still incredibly dense, meaning particles were constantly colliding with unimaginable energy. It was a chaotic, high-energy particle accelerator on a universal scale. In this frenzy, protons and neutrons could get close enough for the strong nuclear force, which operates only at extremely short distances, to grab hold and lock them together. The first and simplest reaction was the fusion of a single proton and a single neutron, creating a nucleus of deuterium, also known as heavy hydrogen. This was the crucial first step, the bottleneck upon which all further creation depended. For a short while, deuterium nuclei were as quickly broken apart by high-energy photons as they were formed. But as the universe cooled past the 1 billion degree mark, this deuterium bottleneck was finally broken. The photons no longer had enough energy to shatter the bonds, and deuterium could accumulate in significant amounts. Once deuterium was stable, a rapid sequence of nuclear reactions unfolded. Deuterium nuclei collided with more protons and neutrons, building up heavier nuclei. 2 deuterium nuclei could fuse to form a helium nucleus containing 2 protons and 2 neutrons. This process was incredibly efficient. In just a few minutes, nearly all the available neutrons were locked up inside helium nuclei. When the universe cooled further, dropping below the temperature needed for nuclear fusion, the process ground to a halt as abruptly as it began. The great cosmic forge shut down, leaving behind a very specific and predictable mix of elements: about 75% hydrogen nuclei, single protons, 25% helium nuclei, and trace amounts, mere fingerprints of lithium and deuterium that didn't get used up. This primordial abundance is one of the most stunning success stories and confirmations of the Big Bang model. The predictions made by the theory about the amounts of hydrogen, helium, and lithium that should have been created in those first minutes match almost perfectly with the oldest observed abundances in the universe. We see this same ratio in the most ancient stars and in distant, pristine gas clouds that have never been enriched by later generations of stars. It is a fossil record etched into the composition of the cosmos itself. The significance of this event cannot be overstated. For the next several 100 million years, hydrogen and helium were the only building blocks available. Every object in the universe, from the first stars to the largest galaxies, was constructed from this simple 2-element recipe. This nucleosynthesis did more than just create elements. It created the first dramatic imbalance in the universe. Vast clouds of neutral hydrogen and helium gas now filled space, but they were not perfectly smooth. Those tiny density variations imprinted by inflation were still there, and the presence of this mass, this gravitational fuel, meant those slight overdensities could now begin to pull matter in. The creation of atomic nuclei provided the gravitational anchors for the next phase of cosmic evolution. The universe had its first tangible structures, and gravity was ready to get to work, setting the stage for the eventual birth of the first stars and the true dawn of light. With a nuclear forge of Big Bang nucleosynthesis complete, the universe entered a profound and transformative chapter, one defined not by light and heat, but by an almost unimaginable darkness and stillness. This epoch, stretching for hundreds of millions of years, is known as the Cosmic Dark Ages. Picture the cosmos at this time. It has expanded and cooled to a point where it is no longer a brilliant, opaque fireball. The free electrons that once scattered light so effectively have now been captured, forming neutral hydrogen atoms with protons during the event known as recombination. For the first time, photons could travel freely across vast distances, and the universe became transparent, releasing the flash of light we now detect as the cosmic microwave background. But as that primordial glow red shifted into invisibility, no new sources of illumination switched on to take its place. The universe was plunged into a deep, pervasive gloom, a vast and silent sea of featureless gas. This was not, however, a period of true inactivity or uniformity. Hidden within that pervasive darkness were the faint blueprints for all future structure, the subtle density variations that inflation had imprinted onto the fabric of the cosmos. Imagine a perfectly calm, foggy night where the mist appears utterly uniform to your eye. Yet, if you could measure the density of the water droplets with immense precision, you would find tiny, random variations. Some patches are a fraction of a percent denser than others. The universe during the Dark Ages was precisely like this. Those regions of slightly higher density, now made of neutral hydrogen gas, held a tiny bit more mass. And according to the law of gravity, more mass means a stronger gravitational pull. This is where the magic and the patience of cosmology comes into play. Gravity is an incredibly weak force, but it is relentless and cumulative. Over millions of years, these slightly denser patches began to exert a faint additional pull on the surrounding gas. Atoms of hydrogen from the less dense regions were ever so slowly drawn toward these gravitational seeds. As matter gathered, the density of these patches increased, which in turn strengthened their gravitational pull, allowing them to draw in even more matter. This process, known as gravitational instability, is a powerful positive feedback loop. It's a cosmic snowball effect where a tiny initial advantage compounds over astronomical timescales. The seemingly uniform darkness was in fact a canvas upon which gravity was quietly, imperceptibly beginning to paint the first outlines of the cosmic web. The growth of these structures was a delicate race against the continuing expansion of the universe. The overall Hubble expansion was trying to pull everything apart, diluting the density of the gas and making it harder for gravity to clump things together. For gravity to win, a region needed to reach a critical threshold of density. Once a cloud of gas reached that point, it decoupled from the expansion of the universe and began to collapse under its own weight. These collapsing clouds were the protogalactic fragments, the dark cradles that would eventually form the first stars and galaxies. They were still invisible, shrouded in darkness, their internal temperatures not yet high enough to ignite the fires of nuclear fusion. For nearly 200 million years, the universe was a silent nursery, nurturing these nascent structures in the dark, their growth governed by the patient, unwavering force of gravity and the initial conditions set in the first fraction of a second after the Big Bang. This quiet era was the essential incubation period, the necessary prelude to the forthcoming cosmic dawn, when the darkness would finally be shattered by the birth of the first brilliant stars. After hundreds of millions of years of profound darkness, the universe was finally poised for its most dramatic transformation yet. Deep within those massive, collapsing clouds of primordial hydrogen and helium, the final act of gravitational collapse was underway. As these dense pockets of gas continued to shrink under their own immense weight, their cores were subjected to ever-increasing pressure and temperature. For eons, the energy from this gravitational contraction was simply radiated away as faint, invisible heat. But there is a fundamental limit to how much matter can be compressed. Eventually, the core temperature within these first protostars soared past 10 million degrees, crossing a critical thermonuclear threshold. In that instant, the oppressive silence of the Dark Ages was shattered as protons, the nuclei of hydrogen atoms, began violently slamming into one another with enough force to overcome their mutual electromagnetic repulsion. The strong nuclear force could finally take over, fusing them into deuterium and then into helium, releasing a torrent of energy in the process. The first star had ignited and the cosmic dawn began. These first stars, known to astronomers as population 3 stars, were unlike anything that exists in the present-day universe. They were true cosmic titans, behemoths forged from a pristine recipe of only hydrogen and helium. Without any heavier elements to help radiate away heat during their formation, the collapsing gas clouds could accumulate far more mass before stabilizing. Theorists suggest these pioneers were monstrously large, potentially hundreds of times more massive than our own Sun. Their incredible mass dictated every aspect of their existence. The immense gravitational pressure at their cores made them extraordinarily hot and luminous, burning their nuclear fuel with a ferocious and desperate intensity. A star that massive lives a short, spectacular life, blazing with the brilliance of millions of suns but destined to exhaust its fuel in just a few million years. A mere cosmic blink of an eye compared to the multi-billion-year lives of smaller stars like our own. The ignition of these first stars did far more than simply fill the universe with light. It initiated the process of cosmic chemical enrichment, forever changing the composition of the cosmos. In their ultra-hot cores, nuclear fusion proceeded at a breakneck pace, forging elements heavier than helium for the very first time. Through processes like the triple alpha reaction, helium nuclei were fused into carbon. In the most massive of these stars, fusion didn't stop there. It created a layered onion-like structure with successive shells fusing elements all the way up to iron. This was a universe-altering achievement. For over 13 billion years, the periodic table had consisted of just 3 simple entries: hydrogen, helium, and a trace of lithium. Now, for the first time, the universe was learning how to build complexity, creating the essential atomic ingredients for future planets and ultimately for life itself. The death of these first stars was as consequential as their birth. Their short, violent lives culminated in spectacular supernova explosions of unprecedented power. These cataclysmic events blasted the newly forged elements carbon, oxygen, nitrogen, iron, and more out into the surrounding space, seeding the pristine hydrogen and helium gas with the first metals. This polluted the virgin gas clouds from which the next generation of stars would form. Furthermore, the shock waves from these titanic explosions likely compressed nearby gas clouds, triggering the collapse and formation of even more stars and the first protogalaxies. This cycle of star birth, life, death, and rebirth began to accelerate, creating a feedback loop of star formation and chemical enrichment that would gradually build up the complex structures we see today. The universe was no longer a simple 2-element system. It was becoming a rich chemical tapestry, and the first stars were the master weavers. The silent, patient work of gravity during the Dark Ages, fueled by the first starlight, set the stage for its most magnificent achievement, the assembly of galaxies. These vast islands of stars, gas, and dark matter represent the most dramatic triumph of order over the universe's chaotic beginnings. They are not random scatterings of stars but highly organized structures with distinct shapes, motions, and histories, each one a testament to the relentless, compounding power of gravity acting upon those ancient quantum seeds. The process began with the dark matter halo. This invisible scaffold is the true architectural foundation of every galaxy. Because dark matter does not interact with light or normal matter through electromagnetic forces, it was unaffected by the pressure of radiation in the early universe. This allowed it to start collapsing under its own gravity long before normal matter could. These halos formed first, creating deep gravitational wells in the fabric of space-time. Ordinary matter, the hydrogen and helium gas enriched by the first stars, then simply followed the blueprint laid out by this dark matter skeleton. As gas clouds were drawn into these growing halos, they began to spin, flatten, and cool, eventually collapsing to form the dazzling disks of stars we recognize as spiral galaxies like our own Milky Way. In other regions where the collapse was more violent and rapid, the gas didn't have time to settle into an orderly rotation, instead forming the giant, ellipsoidal swarms of stars we call elliptical galaxies. The type of galaxy that emerged was determined by the initial conditions of its collapse, the mass, spin, and merger history of its dark matter halo. This transformation from a faint, nearly imperceptible density fluctuation into a brilliant city of stars is a story of amplification on an almost incomprehensible scale. The density variations imprinted by inflation were tiny, on the order of 1 part in 100,000. That's like a single extra grain of sand scattered across an entire beach. Gravity took that minuscule imbalance and magnified it over hundreds of millions of years, patiently gathering material until that one extra grain became a mountain. A region that was only 0.5% denser than its surroundings eventually evolved into a galactic cluster containing thousands of galaxies. The randomness of the initial quantum fluctuation was not erased. Instead, it was channeled and organized by the deterministic laws of physics into a predictable, though incredibly diverse, array of structures. The resulting variety of galaxies we observe today, the majestic spirals with their sweeping arms, the smooth and reddened ellipticals, the irregular galaxies shaped by violent encounters, is not chaos. It is a rich taxonomy of order, each type telling a different story about the conditions of its birth. A quiet, steady accretion of gas produces a grand design spiral. A major collision between two large spiral galaxies can strip away their delicate structures, leaving behind a massive, featureless elliptical. Even the seemingly random distribution of galaxies across the void is not random at all. Instead, they form a vast cosmic web, a network of filaments and clusters that traces the original distribution of those primordial density fluctuations on the largest scales. This intricate architecture shows that the emergence of order is not a smooth, uniform process, but a complex and sometimes violent competition between gravity's tendency to pull things together and the universe's expansion trying to pull them apart. The galaxies we see are the enduring monuments to gravity's victory in that ancient struggle, the places where chaos was finally and decisively sculpted into lasting, stable form. And yet, for all their monumental scale, galaxies are not the final word in cosmic organization. Deep within the heart of nearly every one of these stellar cities, including our own Milky Way, lies an object of such incredible density that not even light can escape its grasp, a supermassive black hole. It is a profound paradox that these ultimate symbols of destruction, these cosmic vacuum cleaners, are in fact essential architects of order, acting as regulatory engines that shape the very galaxies they inhabit. Far from being mere endpoints, black holes are dynamic players in the cosmic story, their immense gravitational influence reaching far beyond their event horizons to govern the fate of billions of stars. The relationship begins with the black hole's incredible gravity. A supermassive black hole containing millions or even billions of times the mass of our Sun sits at the center of its galaxy like a silent monarch. Its gravitational pull is the anchor around which the entire galaxy forms and evolves. Stars in the central bulge orbit this invisible giant at breathtaking speeds, their velocity betraying the presence of the immense hidden mass. This gravitational dominance helps to maintain the overall structure of the galaxy, ensuring the stability of its core over billions of years. But the black hole's influence extends far beyond simply holding things in place. It acts as a cosmic regulator, controlling the rate of star formation in a delicate balancing act. When vast amounts of gas and dust are drawn inward by the black hole's gravity, they can form an incredibly hot, bright disk of material called an accretion disk. As this matter spirals toward its doom, it is compressed and heated to millions of degrees, releasing tremendous amounts of energy across the electromagnetic spectrum. This is when the black hole transitions from a passive anchor to an active governor. During these periods of intense accretion, the black hole becomes a quasar or an active galactic nucleus, shining with the light of 1,000 galaxies. The energy pouring out from this region doesn't just light up the cosmos. It generates powerful winds and jets of radiation that blast outward through the galaxy. These outflows heat the surrounding interstellar gas, preventing it from cooling down and collapsing to form new stars. In this way, the black hole effectively puts a brake on runaway star formation. Without this regulatory mechanism, a galaxy might burn through its entire reservoir of gas in a short, furious burst of stellar creation, leaving it a barren wasteland of aging stars. The black hole ensures a more measured, sustainable evolution, allowing star formation to proceed at a steady pace over billions of years, which is crucial for the development of stable planetary systems and the potential for life. The most dramatic demonstration of this organizing power occurs through galactic mergers. When two galaxies collide, their central black holes eventually sink to the new center of the merged galaxy through a process called dynamical friction. They then begin a gravitational dance, orbiting each other and slowly spiraling inward. This process pumps enormous energy into the surrounding stars and gas, effectively scattering them and helping to shape the structure of the newly formed elliptical galaxy. Eventually, the two black holes may merge themselves, releasing a titanic burst of gravitational waves, ripples in the fabric of space-time that radiate out across the universe. This incredible event is one of the most energetic processes in nature, and it serves as the final act of reorganization, cementing the structure of the new galactic system. From the largest scales of galactic structure down to the heating of interstellar gas, the supermassive black hole is a fundamental force for imposing order, proving that even in the darkest corners of the universe, destruction and creation are intimately linked in the endless cycle of cosmic evolution. But if the gravity of visible matter alone were the full story, our universe would look nothing like it does today. The majestic spiral galaxies, each a whirlpool of billions of stars, present a profound mystery. According to the laws of motion and gravity, the stars on the outer edges of these galaxies should be moving much more slowly than those near the bright center. Think of our solar system. Mercury, the planet closest to the Sun, zips around at a blistering pace, while distant, icy Neptune plods along in a slow, stately orbit. This is how gravity works, yet when astronomers measured the rotational speeds of stars in distant galaxies, they found something astonishing and inexplicable. Stars on the outskirts were orbiting just as fast as those near the core. The galaxies were spinning so rapidly that the gravity from all their visible stars, gas, and dust should not have been nearly strong enough to hold them together. They should have flown apart long ago, their stars scattered into the dark void. This glaring discrepancy could only mean one thing. There had to be far more matter in the galaxy than we could see, a vast quantity of invisible mass whose gravity was the only thing providing the extra glue to keep these cosmic structures intact. This missing mass, this invisible gravitational anchor, is what we now call dark matter. Dark matter is the universe's hidden architect, the unseen framework upon which all visible structure is built. We cannot see it because it does not interact with light or any other form of electromagnetic radiation. It neither emits, absorbs, nor reflects photons. It is utterly transparent, yet it exerts a powerful gravitational pull, and it is this pull that guided the evolution of the cosmos from its earliest moments. Because dark matter is unaffected by the pressure of light and radiation that buffeted normal matter in the hot, dense early universe, it was able to start clumping together long before ordinary atoms could. While the intense radiation of the Big Bang's aftermath kept regular matter spread out in a smooth, hot plasma, dark matter was free to begin collapsing under its own gravity, forming vast, invisible halos and an intricate cosmic web of filaments. These dark matter structures became the gravitational wells, the templates, into which the visible universe would later flow. when the universe finally cooled enough for atoms to form and light to travel freely, the ordinary matter, the hydrogen and helium gas, simply fell into the pre-existing gravitational traps laid out by the dark matter. The galaxies we see today are not the structures themselves. They are the illuminated ornaments hanging on an immense, invisible Christmas tree of dark matter. The evidence for this dark scaffolding is not limited to the rotation of galaxies. We can literally map its presence by observing how its immense gravity bends the very fabric of space-time, an effect known as gravitational lensing. When light from a distant galaxy travels through the universe on its way to our telescopes, its path is subtly warped if it passes near a massive object like a galaxy cluster. By measuring this distortion, astronomers can calculate the total mass of the object doing the bending. Time and again, these measurements reveal that the visible galaxies in a cluster account for only a tiny fraction of the total mass present. The overwhelming majority is this invisible dark matter, whose gravitational field acts as a colossal lens, magnifying and distorting the images of background galaxies into faint, smeared arcs of light, a ghostly signature of the unseen mass. This mysterious substance is not some minor component of the cosmos. It is the dominant form of matter, making up about 85% of all matter in the universe. Its presence is the fundamental reason our universe is structured and not formless. Without the immense gravitational wells carved out by dark matter, the slight density variations from the inflationary epoch would have been far too weak to gather the diffuse gas of the early universe. The expansion of space would have diluted everything before gravity could get a proper foothold, preventing the collapse of gas clouds and the birth of the first stars. There would be no galaxies, no stars, no planets, just a cold, expanding haze of hydrogen and helium. Dark matter provided the essential seed, the initial concentration of gravity that could overcome the universe's expansion and begin the patient work of construction. It is the silent, invisible director of the cosmic orchestra, conducting the movements of visible matter to create the grand and ordered symphony of galaxies we observe across the deep reaches of space and time. And so we arrive at the final and perhaps most profound piece of the cosmic puzzle. Just as dark matter acts as the invisible sculptor pulling the universe together, another, even more enigmatic force is working in the opposite direction, pushing the cosmos apart on the grandest scales. This force is dark energy, and its discovery in the late 1990s sent shockwaves through the world of cosmology, completely reshaping our understanding of the universe's past, present, and ultimate destiny. For decades, the prevailing assumption was that the universe's expansion, set in motion by the Big Bang, must be slowing down. After all, gravity is an attractive force. Every galaxy, every cluster, every bit of matter exerts a gravitational pull on every other bit. It seemed logical that this collective gravity would act as a cosmic brake, gradually decelerating the expansion over billions of years. Astronomers set out to measure this expected slowdown by observing distant supernovae, using them as standard candles to gauge the expansion rate of the universe across vast distances and back in time. What they found was not a slowdown, but the exact opposite. The expansion of the universe is not decelerating, it is accelerating. The fabric of space-time is being stretched apart at a faster and faster rate. Some unknown form of energy permeating the vacuum of space itself is overwhelming the collective gravitational pull of all the matter in the cosmos and driving this accelerating expansion. This mysterious repulsive force was dubbed dark energy. So what is it? The leading candidate is something known as the cosmological constant, a concept Einstein originally introduced and later called his biggest blunder to create a static universe in his equations. It represents a constant energy density that is an inherent property of the vacuum of space itself. As the universe expands and more space comes into existence, more of this dark energy appears, creating a feedback loop that drives the expansion ever faster. Think of it as an anti-gravity force, a kind of cosmic pressure that is woven into the very fabric of reality. While its nature remains one of the biggest mysteries in physics, its influence is undeniable and colossal. Dark energy is thought to constitute about 70% of the total mass energy content of the universe, making it the dominant component of the cosmos. This accelerating expansion has a profound organizing effect on the largest scales of the universe, shaping the cosmic web we see today. In the past, when the universe was smaller and denser, gravity had the upper hand. It pulled matter into the filaments and nodes of the web, creating the great walls and clusters of galaxies. But as the universe has expanded and dark energy has come to dominate, it has begun to change the rules of the game. Dark energy acts as a kind of cosmic zoning law, effectively putting a limit on how large structures can grow. It makes it more difficult for gravity to pull matter together across vast distances. While the tightly bound structures like individual galaxies and galaxy clusters will remain held together by their own gravity, the spaces between these structures are being stretched ever wider. The cosmic web is not being torn apart, but its future growth is being stifled. Dark energy is determining the final, frozen architecture of the universe. This leads us to the ultimate fate of the cosmos, a future shaped entirely by the relentless push of dark energy. In a scenario often called the Big Freeze or heat death, the acceleration will continue indefinitely. Over hundreds of billions of years, galaxies outside our local gravitationally bound group will be pushed away by the expansion faster and faster. Their light red shifted into invisibility until they disappear beyond our cosmological horizon. The universe will become a much darker and lonelier place. Star formation will eventually cease as the interstellar gas needed to form new stars becomes too diffused to collapse. Existing stars will burn out and galaxies will fade to black. The universe will be left as a cold, ever-expanding emptiness, dotted with the dead remnants of stars and black holes, which themselves will eventually evaporate over unimaginable timescales thanks to Hawking radiation. Dark energy, the mysterious organizer, will have structured the universe into its final, silent, and eternal form, a vast, dark, and empty cosmos, a permanent monument to the brief, brilliant flash of complex order that once emerged from chaos. This journey from a formless, chaotic beginning to a cosmos brimming with galaxies, stars, and planets leads us to a question so profound it borders on philosophy. Why does our universe seem so perfectly set up for this outcome? The laws of physics, the strengths of the fundamental forces, the initial conditions of the Big Bang, they all appear to be exquisitely fine-tuned. If the strength of the strong nuclear force were just a few % different, protons could not bind together and atomic nuclei would never have formed. If the force of gravity were slightly stronger, the universe would have collapsed back on itself almost immediately. If it were slightly weaker, matter would never have clumped together into stars and galaxies. The expansion rate of the universe had to be balanced on a razor's edge. This incredible precision, where seemingly arbitrary constants have just the right values to allow for complexity and life, is known as the fine-tuning problem. One compelling way to approach this puzzle is through the anthropic principle. In its simplest form, this principle states that the universe must be compatible with the conscious life that observes it. We should not be surprised to find ourselves in a universe that permits our existence, because in a universe that did not, we would not be here to ask the question. It is a selection effect. Imagine a puddle waking up one morning and marveling at how perfectly the hole it occupies fits its shape. The puddle thinks the hole must have been designed precisely for it, not realizing that it is simply conforming to the shape of the hole. In a similar way, we may find the constants of nature perfectly suited for life because life is a product of those constants, not the other way around. This logical observation, however, doesn't fully explain why this particular set of constants exists. This is where the concept of a multiverse enters the discussion. If our universe is just one bubble in a vast, perhaps infinite multiverse, each with its own random set of physical laws and constants, then fine-tuning is no longer a miracle but a statistical inevitability. In an infinite ensemble of universes, every possible combination of physical parameters will be realized somewhere. We simply find ourselves in one of the rare habitable universes where the numbers worked out. In this view, our emergence from chaos was not preordained, but neither was it a singular, impossible fluke. It was simply our number coming up in a cosmic lottery with an immense number of tickets. The multiverse idea, while speculative, is a natural extension of theories like eternal inflation, which suggest that the rapid expansion of spacetime can be a perpetual process, continually spawning new pocket universes with different properties. It transforms the question from why are the laws of physics so perfect to what mechanisms generate this diversity of universes. Yet, this proposed solution also raises its own deep philosophical questions. If a theory predicts an infinite number of unobservable universes, can it ever be truly tested? Some argue it moves beyond the realm of science into metaphysics, while others point to the fine-tuning itself as indirect evidence for a broader reality. Another perspective considers whether this apparent fine-tuning might point to a deeper, underlying theory where these constants are not arbitrary, but are necessarily what they are, the only possible outcome of a more fundamental law of nature. Just as the number pi is not an arbitrary value but emerges from the geometry of a circle, perhaps the constants we observe are the only ones that could emerge from the mathematical structure of reality. Our journey from quantum chaos to cosmic order might not have been a random roll of the dice, but the inevitable unfolding of a profound and beautiful mathematical truth, a universe that could not have been any other way. Whether through a vast multiverse, a deeper unity, or sheer incredible fortune, the fact that we are here to ponder it remains the most captivating mystery of all. Captured in every direction we point our radio telescopes, there is a faint, cold whisper of radiation that permeates the entire cosmos. This is the cosmic microwave background, or CMB, and it is arguably the most important fossil ever discovered. It is the afterglow of the Big Bang itself, a snapshot of the universe frozen in time when it was a mere 380,000 years old. Before this moment, the universe was an opaque, searing plasma, so dense that light particles or photons were constantly bouncing off a thick fog of free electrons, unable to travel in a straight line. But as expansion drove the temperature down, a monumental event occurred called recombination. Protons and electrons finally had a chance to combine and form the first stable hydrogen atoms. For the first time, the fog lifted, the universe became transparent, and those once trapped photons were suddenly set free on a journey across the cosmos. Today, we detect that ancient light as a microwave signal, cooled and stretched by the expansion of the universe over 13.8 billion years to a temperature of just 2.7 degrees above absolute zero. But the CMB is far more than a uniform blanket of cold radiation. When we analyze it with incredible precision, we find it is not perfectly smooth. It is imprinted with tiny, random variations in temperature minute fluctuations on the order of 1 part in 100,000. These are the faint hot and cold spots, regions that were ever so slightly denser or less dense than their surroundings. This minute modeling is the baby picture of our cosmos, and it is the most direct evidence we have of the primordial chaos from which everything emerged. Those tiny imperfections are the gravitational seeds that inflation amplified from quantum fluctuations. This cosmic blueprint tells a precise story of transition. The pattern of these hot and cold spots is not random noise. It holds encoded information about the contents and geometry of the entire universe. By meticulously measuring the statistical properties of these fluctuations, cosmologists can read this ancient code. The sizes of the spots reveal the conditions of the early universe, confirming that it was geometrically flat, just as inflation predicted. The specific distribution of these variations allows us to calculate the precise recipe of the cosmos: about 5% ordinary matter, 27% dark matter, and 68% dark energy. The CMB is therefore a complete inventory of the universe, a fossil that tells us not only what the infant cosmos looked like, but what it was made of. Most profoundly, these tiny temperature differences correspond directly to the density variations that would shape the future. A slightly warmer region in the CMB indicates a spot that was marginally denser. The extra mass in that area created a slightly stronger gravitational pull, a small hill in the fabric of spacetime. Over the eons that followed, this gravitational advantage allowed these regions to pull in more and more matter from their surroundings. The slightly denser patches grew into vast clusters of galaxies, while the slightly less dense regions evolved into the immense cosmic voids we see today. The entire large-scale structure of the modern universe, the great glittering filaments of the cosmic web, and the dark, empty spaces between them, is simply an enormously magnified version of that subtle pattern etched onto the CMB. This faint echo of creation is the ultimate link between the quantum chaos of the beginning and the majestic order of the present, providing undeniable proof that our complex cosmos was born from the faintest whispers of randomness. Yet, for all their grandeur, galaxies are not the final destination in this journey from chaos to order. The same processes that forged stars and assembled galaxies on a cosmic scale also operated on a much more intimate level, giving rise to the intricate architectures of solar systems. Our own solar system, with its stately procession of planets orbiting a central star, is a stunning example of this local organization emerging from a much smaller, but no less chaotic, beginning. Its story starts not with a bang, but with a gentle, almost imperceptible drift within a massive molecular cloud. These vast clouds, the nurseries of stars, are scattered throughout galaxies like our Milky Way. They are cold, dark, and tenuous, composed mostly of hydrogen and helium gas peppered with fine dust grains, the heavy elements forged in the hearts of long-dead stars. For the most part, these clouds are stable, with internal gas pressure balancing the gentle pull of their own gravity, but they are not perfectly uniform. A passing shockwave from a nearby supernova explosion, or the gentle squeeze of a spiral galaxy's density wave, can disturb this delicate balance. In one particular region of the cloud, a pocket of gas and dust becomes just a fraction denser than its surroundings. This tiny advantage is all gravity needs to begin its work. Over millions of years, this denser region begins to pull in more material from the cloud, growing in mass and gravitational influence. As it collapses, the cloud fragment begins to slowly rotate, a spin imparted by the random motions within the original cloud and conserved as the cloud shrinks, causing it to rotate faster, much like a figure skater pulling in their arms. The center of this collapsing cloud grows denser and hotter, becoming a protostar, a nascent sun shrouded in a thick, spinning disk of gas and dust known as a protoplanetary disk. This disk is the raw material from which planets will form. It is a chaotic environment, a whirling maelstrom of particles constantly colliding. Within this disk, the first step toward order is accretion. Microscopic dust grains coated in icy mantles begin to stick together when they collide, first through static forces and then through simple gravity. These tiny clumps grow into larger pebbles, then rocks, and then kilometer-sized bodies called planetesimals. These are the building blocks of planets, and their formation marks a critical turning point. The random, chaotic collisions within the disk are now channeled into a process of systematic growth. Gravity now takes over completely. The largest planetesimals have the strongest gravitational pull, allowing them to dominate their orbital zones. They act as gravitational anchors, sweeping up smaller planetesimals and dust in their path, growing rapidly into planetary embryos and then into protoplanets. This stage is a period of violent chaos on a local scale, a gravitational demolition derby where countless collisions and mergers shape the final planets. The inner disk, hot from the energy of the forming star, is dominated by rocky and metallic materials that can remain solid at high temperatures. This is where the terrestrial planets Mercury, Venus, Earth, and Mars are forged from rock and metal. Further out, beyond the frost line where temperatures are cold enough for volatile ices to exist, a different process unfolds. Here, protoplanets can accumulate not just rock and metal, but also vast amounts of frozen water, ammonia, and methane. This allows them to grow to immense sizes, becoming the cores of the gas giants. Once these cores reach a critical mass about 10 to 15 times the mass of Earth, their gravity becomes powerful enough to directly capture and hold onto the vast reservoirs of hydrogen and helium gas that make up the bulk of the protoplanetary disk. Jupiter and Saturn likely acquired their massive gaseous envelopes in this way. Farther out still, where the material was more sparse and orbital speed slower, Uranus and Neptune formed more slowly, accumulating smaller amounts of gas over longer periods. This entire process, from cloud collapse to mature planets, took less than 100 million years, a blink of an eye on cosmic timescales. A final stage of clearing then ensued. The powerful gravity of the newly formed giant planets, particularly Jupiter, scattered remaining planetesimals everywhere. Some were flung inward, bombarding the inner planets in a period known as the Late Heavy Bombardment, potentially delivering water and organic materials to young worlds like Earth. Others were hurled outward to the distant reaches of the system, forming the Kuiper Belt and the Oort Cloud. The young star's intense solar wind then blew away the remaining vestiges of the gas and dust disk, revealing the newly minted solar system in its essential form. A central star orbited by a family of planets on stable, nearly circular orbits, with a collection of moons, asteroids, and comets as remnants of its chaotic birth. From a formless, drifting cloud, gravity and physics had sculpted a marvel of orbital mechanics, a stable system where the chaos of countless collisions had finally given way to a harmonious and enduring order. Among the countless protoplanets forged in the violent chaos of the early solar system, one rocky world would follow a unique and transformative path, evolving from a molten ball of rock and metal into the stunningly complex and ordered planet we call home. Earth's story is not just one of astronomical formation, but a profound local victory of organization, where the relentless laws of physics carved a stable, layered world out of cosmic disorder. This transformation began with a cataclysm. The young Earth was a hellish place, subjected to a relentless barrage of planetesimals and debris left over from the solar system's formation. The energy from these constant impacts, combined with the decay of radioactive elements within its interior, heated the entire planet to a molten state. For a time, Earth was little more than a global magma ocean, a seething, liquid sphere where heavier elements like iron and nickel could no longer resist the pull of gravity. This period of complete melting was the crucial first step toward creating order. In a process called planetary differentiation, the materials that made up the early Earth began to separate and organize themselves by density, like different oils and vinegars settling in a bottle. The heaviest elements, primarily iron and nickel, sank through the molten rock toward the center, coalescing to form a dense metallic core. This event was arguably the most important in our planet's history, for it generated Earth's magnetic field. As the liquid outer core churns around the solid inner core, it acts as a colossal dynamo, creating a protective magnetic shield that extends far out into space. This invisible barrier deflects the solar wind, a constant stream of charged particles from the sun that would otherwise strip away our atmosphere and bathe the surface in harmful radiation. Without this organized, layered core, life as we know it would never have had a chance to arise. Meanwhile, the lighter silicate minerals rose to the surface, gradually cooling to form a primitive crust, while the material between the core and the crust settled into the thick, convecting layer we call the mantle. This internal structure, core, mantle, crust, is the fundamental architectural blueprint of our planet. But this organization was not a one-time event. It is a dynamic, ongoing process. The heat from the core and the decay of radioactive elements continue to drive immense geological activity. The mantle slowly churns like a pot of extremely viscous soup, its convection currents providing the engine that drives plate tectonics. The brittle crust is broken into massive plates that float on this malleable mantle, slowly moving, colliding, and recycling material between the surface and the interior. This relentless recycling is not chaos, it is a powerful regulatory system. It stabilizes our climate over geological timescales by regulating the carbon cycle, and it is responsible for creating the continents, the mountains, and the ocean basins, the very stage upon which life would evolve. Yet, a stable geology alone was not enough to create a habitable world. Earth's next great act of organization was the formation of a durable atmosphere and hydrosphere. Our first atmosphere, likely composed of hydrogen and helium captured from the solar nebula, was quickly lost to the solar wind because the young sun was extremely active and our magnetic field was still developing. A second atmosphere then emerged from within the planet itself, vented through countless volcanoes in a process called outgassing. This created a thick blanket of gases, primarily water vapor, carbon dioxide, nitrogen, and sulfur compounds. As the planet's surface continued to cool, a miraculous transition occurred. The water vapor in the atmosphere condensed and fell as rain, but this time the surface was cool enough for it to remain liquid. It rained for thousands of years, slowly filling the low-lying basins to create the first primitive oceans. This was the birth of the hydrosphere, a vast reservoir of water that would become the cradle of life and a crucial moderator of Earth's climate. The final piece of the puzzle was the transformation of that early, toxic atmosphere into one that could support complex life. This incredible feat was achieved not by geology or physics alone, but by the emergence of life itself. The first primitive organisms that arose in the oceans began to harness the energy of the sun through photosynthesis. Their waste product was oxygen, a highly reactive gas that was initially absorbed by iron in the oceans, forming vast bands of iron oxide that settled to the seafloor. After saturating the oceans, oxygen began to accumulate in the atmosphere in what is known as the Great Oxidation Event, an environmental catastrophe for the anaerobic life of the time, but an absolute necessity for the future of complex organisms. This biological process created the third and current atmosphere, a finely tuned mixture of nitrogen and oxygen that shields us from radiation, retains warmth, and provides the essential ingredients for respiration. Life did not just adapt to its environment, it actively participated in creating and maintaining the very conditions for its own survival, locking the planet into a self-regulating, highly organized state of dynamic equilibrium. Earth, therefore, stands as a magnificent testament to the emergence of order on a local scale. From a homogenized mix of solar debris, it differentiated into a structured, layered sphere with a protective magnetic core. From a violent, impact-ridden surface, it developed a stabilizing system of plate tectonics that sculpts continents and regulates climate. From volcanic outgassing, it condensed oceans and an atmosphere, which were then fundamentally altered by the life they nurtured. Each step was a move away from randomness and toward greater complexity and stability. Our planet is a localized pocket of exquisite organization, a rare and precious oasis where the fundamental constants of the universe, the specific conditions of our solar system, and the inherent properties of chemistry and biology all align to transform a chaotic beginning into a world of breathtaking order and beauty. And yet, for all its geological elegance and atmospheric balance, Earth's most profound leap from chaos to order was still to come. The emergence of life represents a qualitative shift in the universe's organizing principles, a moment where inanimate chemistry somehow crossed a threshold to become autonomous biology. This transition is arguably the most dramatic and mysterious emergence of all, where the universe became aware of itself. The raw materials were already present on the young Earth: water, minerals, and an atmosphere rich in gases like methane, ammonia, carbon dioxide, and water vapor, all churning under a constant bombardment of energy from lightning, volcanic heat, and ultraviolet radiation. This chaotic, energetic environment was not a barrier to life's origin. It was the essential crucible. One of the most compelling frameworks for understanding this leap is the concept of self-organization, where complex systems spontaneously develop order out of disorder through the flow of energy. In the 1950s, the Miller-Urey experiment demonstrated this principle in a stunningly simple way. By simulating the conditions of early Earth in a closed apparatus, a mixture of water, methane, ammonia, and hydrogen, subjected to electrical sparks to mimic lightning, they found that within days the clear water turned a murky brown. Analysis revealed this broth was rich in amino acids, the fundamental building blocks of proteins and life itself. This wasn't creating life in a jar, but it powerfully showed how the basic organic molecules necessary for life could arise naturally from non-living ingredients through nothing more than the application of energy to a chaotic mix. The experiment suggested that the emergence of life's chemical precursors wasn't a fantastically unlikely event, but a probable, even inevitable, outcome of planetary chemistry. But amino acids are a far cry from a living cell. The next critical step was moving from a soup of building blocks to a system capable of metabolism, replication, and containment. How did these molecules organize themselves into something that could be considered alive? One leading theory focuses on the emergence of self-replicating molecules, most likely a primitive form of RNA. RNA is a fascinating molecule because it can both store genetic information, like DNA, and catalyze chemical reactions, like a protein enzyme. In an RNA world, a single molecule could have acted as both the blueprint and the builder, copying itself in a messy, error-prone process that allowed for the very first steps of evolution. These replicating RNAs wouldn't have been floating freely for long. Lipid molecules, which have a natural tendency to spontaneously form hollow, cell-like bubbles called vesicles, could have provided the first membranes. These microscopic containers would have offered a huge advantage, creating a protected environment where complex chemistry could occur without being diluted by the vast ocean, effectively creating the first protocells. This shift from independent chemistry to bounded, competing systems marks the true dawn of biology. These protocells weren't yet life as we define it, but they were systems on the cusp. They could grow by incorporating new molecules from their environment and eventually divide through physical stresses like waves or currents. Those that contained more successful, faster replicating RNAs would effectively outcompete their neighbors, representing the most primitive form of natural selection. This is where randomness and chaos once again become the engine for creating order. Random errors in copying mutations introduced variation. Most were detrimental, but occasionally one would provide an advantage, allowing that protocell lineage to persist and multiply. Over unimaginable lengths of time, through this relentless process of competition and selection, these simple systems grew in complexity. They developed more efficient ways to harness energy, likely first from chemical gradients around deep-sea hydrothermal vents, and later learned to capture the energy of the sun through photosynthesis. The genetic code likely standardized, with DNA taking over the more stable role of information storage while proteins became the specialized workhorses of cellular function. The fact that this transition from chemistry to biology occurred relatively quickly on a geological timescale, perhaps within a few 100 million years of the Earth cooling enough to have liquid water. suggests that under the right conditions, the emergence of life might be a natural progression of the universe's organizing principles. It hints that the same drive toward complexity that shaped galaxies and stars also operates on the molecular level. Life, in this view, is not a separate entity imposed upon a dead universe, but an extension of its inherent tendency to create order from chaos when energy flows through a system. The laws of physics and chemistry, given the right ingredients and enough time, seem to inevitably give rise to biology. This doesn't diminish the miracle of life, it elevates it, framing it as a cosmic phenomenon, a universe fulfilling its potential for complexity and consciousness. From the quantum fluctuations of the Planck Epoch to the double helix of DNA, we see a continuous thread of emergence, a universe perpetually discovering new and more beautiful forms of order. And so, from the intricate chemistry of early Earth, a new and breathtaking form of order emerged, life. But life, in its earliest forms, was a purely reactive phenomenon. Organisms responded to stimuli, grew, and reproduced, all governed by intricate biological programming. For billions of years, the universe was filled with activity but devoid of any inner experience. Then, somewhere along the evolutionary path, something revolutionary occurred. Within the complex neural networks of certain animals, a new property flickered into existence: subjectivity. The raw data of sensory input was no longer just processed, it was felt. This was the dawn of consciousness, the moment the chaotic, physical universe, through the incredible organized complexity of life, finally awoke and became aware of itself. This emergence of an inner world from mere matter is perhaps the deepest mystery we face. How does the objective firing of neurons' electrical impulses and chemical exchanges give rise to the subjective richness of a feeling? How does the warmth of sunlight on skin, the bitter taste of lemon, or the profound ache of sadness arise from a collection of atoms? This is what philosophers call the hard problem of consciousness. We can map every neural pathway, understand every neurotransmitter, and yet that gap between the physical mechanism and the personal experience seems unbridgeable by our current science. It suggests that consciousness is not just a more complex version of information processing. It is a fundamentally different kind of phenomenon, an entirely new layer of reality that manifested when biological complexity crossed a critical and still unknown threshold. This has profound philosophical implications. If mind truly emerges from matter, then it forces us to reconsider the very nature of reality. For a long time, a perspective known as dualism held sway, which proposed that the mind or soul is a separate, non-physical substance distinct from the physical body. But the scientific evidence increasingly points the other way. We know that altering the brain with chemicals, trauma, or disease directly alters consciousness itself. This supports a view of monism that everything, including mind, is derived from the physical world. In this view, consciousness isn't a separate entity that the brain produces. It is what the brain's specific, highly organized activity is. It is an intrinsic property of certain complex systems, a new level of order that emerges from the chaos of countless neural interactions, much like the wetness of water emerges from the collective behavior of H2O molecules, even though no single molecule is wet. This means that we and every other conscious being are the universe's way of knowing itself. The hydrogen atoms forged in the Big Bang, the carbon atoms cooked in the heart of long-dead stars, have, after billions of years of cosmic evolution, organized themselves in such a way that they can now contemplate their own origins. Through our eyes, the universe observes its own galaxies. Through our minds, it ponders its own laws. We are not just inhabitants of the universe, we are a part of its ongoing process, the point at which the cosmos has developed self-awareness. Our curiosity, our drive to understand the chaos from which we came, is not separate from the universe. It is the universe seeking to understand its own story. In this light, our existence is not a random accident in an indifferent void, but a deeply meaningful event, the awakening of cosmic chaos into conscious order. This remarkable journey from unconscious matter to conscious mind leads us to a final, deeply personal mystery that underpins our entire experience of reality, the relentless and irreversible flow of time. We all feel it intuitively. Time has a direction. We remember the past but not the future. We age, we change, and we cannot undo what has been done. This one-way street is known in physics as the arrow of time, and its origin is deeply tied to the very same cosmic story of emerging order that we have been tracing from the Big Bang onward. At its heart, the arrow of time is a story about probability and memory, written into the fabric of the universe from its very first moment. The fundamental laws of physics, from Newton's mechanics to Einstein's relativity and even quantum theory, are almost entirely time-symmetric. This means that if you were to take a video of any microscopic interaction, two particles colliding, for instance, and play it backwards, the reversed action would also obey the laws of physics. There is no inherent past or future in the equations, yet our macroscopic experience is overwhelmingly one-way. The reason for this disconnect lies in the second law of thermodynamics and the concept of entropy, which we can think of as the degree of disorder or randomness in a system. The second law states that the total entropy of an isolated system always increases over time. It is this statistical tendency toward disorder that gives time its arrow. A shattered glass does not spontaneously reassemble. Ice melts in a warm room. Perfume diffuses to fill an entire space. These processes are irreversible because they move from a state of lower probability to a state of higher probability. There are vastly more ways for a system to be disordered than ordered, but this presents a fascinating paradox. If the universe is inevitably moving toward a state of maximum entropy, a featureless heat death, how do we explain the breathtaking local increases in order we see all around us? How did complex structures like galaxies, stars, planets, and life itself emerge from the primordial chaos? The answer is that these pockets of order are not violations of the second law. They are a direct consequence of it, but they come at a cost. When a star forms, drawing scattered gas into a tight, organized sphere, it is creating a local region of very low entropy, but the process of fusion in its core releases a tremendous amount of heat and light, which radiates out into the universe, increasing the overall entropy of the cosmos far more than the order created within the star. The same is true for a plant using photosynthesis to grow, or for your own body maintaining its intricate structure. Every single local act of ordering, of creating complexity, is paid for by a net increase in disorder elsewhere. We are all engines of entropy, creating small islands of order by exporting chaos into our surroundings. This is why we remember the past and not the future. Our brains, and indeed all recording devices, are essentially entropy detection machines. Memory formation is a physical process that involves a change in the state of our neurons. For a memory to be created, a causal chain of events must occur that leaves a lasting, ordered imprint on our brain tissue. This imprint is only possible because the universe started in a state of incredibly low entropy, the highly ordered, low entropy initial conditions of the Big Bang. That initial state provides the foundation for all the complex, irreversible processes that follow. It is the reason why causes always precede effects. We can remember the past because the past is the state that left an ordered imprint on our present. The future, by contrast, is a state of higher entropy, and it hasn't happened yet to leave any such mark. Our perception of time's flow is, in a very real sense, our perception of the universe's ongoing journey from its uniquely ordered beginning toward its probable disordered end. In this grand cosmic context, our lives gain a profound new meaning. The arrow of time is not a cruel master pushing us toward decay, but the very condition that makes change, growth, and experience possible. It is the reason stories have a beginning, middle, and end. It is the reason evolution can build complexity over eons. It is the reason our choices matter, because they are irreversible. We are not passive observers of time's flow. We are active participants in the universe's great project of transforming its initial order into a rich tapestry of complex structures and experiences, all while faithfully obeying the deep statistical truth that guides it from past to future. Our consciousness, our memories, and our very sense of a progressing present are all gifts bestowed by that singular, low-entropy spark at the dawn of everything. This extraordinary journey from the first particles to conscious minds invites a profound question. Is the rise of complexity a fundamental, inevitable trend written into the laws of the universe, or is it simply a fleeting, local accident? The evidence we see around us is compelling. Over 13.8 billion years, the cosmos has seemingly progressed from a near-featureless soup of energy to a reality teeming with intricate structures, galaxies, stars, planets, life, and consciousness. This grand narrative suggests a universe with an inherent creative potential, a natural drive toward building ever more complex and ordered systems from its chaotic beginnings. This apparent trend is powered by a combination of the universe's expansion and the relentless compounding work of its fundamental forces. The initial expansion created the cooling and the space necessary for structures to form without being immediately torn apart. Gravity then acted as the great gatherer, patiently amplifying those tiny quantum seeds into galaxies and stars. Within those stars, nuclear forces forged the heavier elements, expanding the periodic table and providing the raw ingredients for everything more complex than hydrogen and helium. On planets like Earth, chemistry governed by electromagnetism could experiment with these ingredients, eventually stumbling upon self-replicating systems that gave rise to biology. At each stage, the products of the previous level become the building blocks for the next, creating a ladder of increasing sophistication. However, we must be cautious not to confuse this local story with a universal law. The second law of thermodynamics still reigns supreme, stating that the overall entropy or disorder of the entire universe is always increasing. The creation of these localized pockets of exquisite order from a star to a brain always comes at a cost. That cost is an even greater increase in disorder elsewhere. A star creates its beautiful, ordered structure by radiating vast amounts of disordered heat out into the void. A living organism maintains its complex internal order by consuming energy from its environment and expelling waste, increasing the entropy of its surroundings. We are magnificent temporary eddies in a vast river flowing inexorably toward a more probable disordered state. So is the emergence of complexity a fundamental trend? The answer is nuanced. It is not a law that overrules thermodynamics, but rather a probable outcome within a universe that began in a very specific, highly ordered low-entropy state. Given that starting point, the laws of physics make the formation of some complex structures not just possible, but almost inevitable. Gravity will inevitably clump matter. Under the right conditions, chemistry will inevitably create interesting molecules. Given enough time and a stable environment, self-replication and evolution may well be a natural progression. The trend toward complexity is not a mysterious force pulling the universe upward. It is a natural cascading consequence of the initial conditions playing out under the reliable rules of physics, creating islands of order in a sea of increasing chaos. This means our existence is both spectacular and statistically fragile. We are the beneficiaries of a very particular cosmic history, a chain of events that allowed complexity to flourish in our corner of the universe. Whether this same chain has unfolded elsewhere is one of science's great questions, but here on Earth it has allowed the universe to achieve something remarkable. It has become conscious of itself. Through us, the cosmos can reflect on its own origins, trace its own history, and marvel at its own laws. The evolution from simplicity to complexity is the story of how a chaotic beginning gave rise to a reality capable of understanding its own chaos, and in doing so, finding a deep and profound sense of order. Looking ahead across timescales that dwarf human history, the future evolution of cosmic structure is a tale of two competing forces: the relentless local pull of gravity and the growing global push of dark energy. For billions of years, gravity has been the master architect, but its reign is gradually coming to an end. On relatively short timescales, measured in mere hundreds of millions of years, gravity will continue to build structure through a violent and spectacular process: galactic collisions. Our own Milky Way is on a direct collision course with the neighboring Andromeda Galaxy. In about 4.5 billion years, these two great spiral galaxies will begin a gravitational dance that will utterly transform them. They will not simply crash and burn. Instead, they will pass through each other, their structures stretched and distorted by immense tidal forces, triggering ferocious waves of new star formation as clouds of gas are compressed. After a series of close passes, they will eventually merge, their stars and dark matter halos coalescing into a single, giant elliptical galaxy. This fate is not unique. Across the universe, galaxies within local groups are destined to merge, creating larger and larger elliptical galaxies. These cities of stars will grow, but their distinct spiral structures, born from orderly rotation, will be erased forever in these cosmic demolition derbies. While gravity reshapes galaxies on a local level, dark energy is dictating the fate of the universe on the largest scales. The acceleration of the universe's expansion, driven by this mysterious energy, is like a cosmic zoning law that will eventually forbid any new large-scale structures from forming. Right now, galaxies that are not already bound together by gravity in groups and clusters are being pushed apart by the stretching of space itself. As the expansion accelerates, the distance between these gravitationally unbound structures will increase at a rate that eventually surpasses the speed of light. This doesn't violate relativity, as it is space itself that is expanding faster than light can traverse it. The consequence is that those distant galaxies will one day disappear from our view entirely, their light unable to ever reach us again. For any future astronomers in our local gravitationally bound group, which includes the merged Milky Way Andromeda Galaxy and a few dozen smaller galaxies, the observable universe will shrink dramatically. The cosmos will appear as a single, giant galaxy adrift in an immense and ever-growing sea of black, empty space. The great cosmic web, the large-scale structure we see today, will fade from view, its patterns frozen and isolated. This leads to the long-term fate of all stars and ultimately all matter. The accelerating expansion will not tear apart individual galaxies or solar systems, as their internal gravity is strong enough to hold them together. But it will drastically alter their environment. As galaxies merge and use up their remaining gas, the era of star formation will slowly draw to a close. The last stars to form will be small, dim red dwarfs, which burn their fuel so slowly they can shine for trillions of years. But even they will not last forever. One by one, stars of all sizes will exhaust their nuclear fuel. Some will end as cooling embers known as white dwarfs. Others will explode, leaving behind neutron stars or black holes. Over almost unimaginable timescales, even the structure of galaxies will begin to erode. The random gravitational interactions between stars and stellar remnants can slowly fling them out into the intergalactic void, a process called dynamical evaporation. What remains will be a slowly tightening cluster of black holes at the galaxy's center, which may themselves eventually merge through the emission of gravitational waves. The final state, often called the heat death or the big freeze, is one of ultimate equilibrium but also of profound stillness. In this distant future, the universe will be a cold, expanding near vacuum. The few remaining particles will be so spread out that collisions between them become exceedingly rare. the temperature will approach absolute zero everywhere. Black holes, once the engines of galactic organization, will not be permanent features. Through a quantum process predicted by Stephen Hawking, they will very slowly evaporate, radiating away their mass until they too pop out of existence. With the evaporation of the last black hole, the universe will reach its final state. There will be no more energy gradients, no hot places or cold places, no structures of any kind, just a thin, uniform soup of photons and subatomic particles, forever expanding and cooling toward absolute zero. This is the ultimate victory of entropy, the final equilibrium where all the work of cosmic organization, from the first stars to conscious life, is erased. It is a bleak but statistically inevitable end, the final chapter in the story that began with a low entropy spark. Yet, within this grand narrative, our fleeting moment of existence, where we can observe and comprehend this magnificent cosmic story, becomes all the more precious and profound. We stand at a unique crossroads in this cosmic story, not merely as products of emergence but as its conscious agents. For billions of years, the universe organized itself through mindless physical processes. Gravity clumped matter, stars forged elements, and chemical reactions eventually sparked life. But with the arrival of human consciousness, a new and remarkable phase may have begun. One where the universe can not only create order but can consciously understand, steward, and even direct it. We are the universe's way of becoming self-aware, of looking back on its own history and peering into its own future. This bestows upon us a profound responsibility, a role that extends far beyond our planet and into the broader canvas of cosmic evolution. Our most immediate and tangible responsibility is the preservation and cultivation of order here on Earth. Our biosphere is a breathtakingly complex and delicate system of interconnected order, a localized pocket of low entropy that has been billions of years in the making. Through our intelligence and technology, we have gained the power to either nurture this complexity or unravel it. Climate change, species extinction, and resource depletion are not just environmental issues. They are examples of humanity inadvertently accelerating entropy on a planetary scale. Conversely, practices like sustainable energy, ecosystem restoration, and biodiversity conservation are acts of cosmic maintenance. They represent a conscious effort to uphold the intricate order that evolved naturally, making us not just inhabitants of this planet but its gardeners and guardians. This is our first and most fundamental duty as agents of order, to protect the complex system that allowed us to emerge in the first place, but our role likely doesn't end at Earth's atmosphere. Our drive to explore and understand points toward a future where humanity becomes an active participant in shaping order across the solar system and beyond. This concept, often called cosmological seeding or directed panspermia, suggests that life, and particularly intelligent life, might be the universe's most effective mechanism for fighting back against the tide of entropy on a grand scale. Imagine a future where we purposefully transport microbial life to other worlds, jump-starting evolutionary processes on planets like Mars or the moons of Jupiter and Saturn. We would be acting as a catalyst, accelerating the universe's inherent tendency toward complexity in environments where it might otherwise take billions of years to occur, or perhaps never happen at all. In this view, spacecraft are not just probes, they are vessels carrying the seeds of order, extending the chain of emergence that began with the Big Bang. This leads to an even more profound possibility: the transition of life from a biological to a post-biological state. The same intelligence that allows us to comprehend quantum mechanics and general relativity may also allow us to transcend our biological limitations. If we can navigate the immense ethical and philosophical challenges, we might one day engineer intelligences that are far more resilient and capable than ourselves, perhaps based on synthetic biology or advanced artificial intelligence. These post-biological entities would not be subject to the frailties of carbon-based life. They could theoretically operate in the harsh environment of space, withstand immense timescales, and process information on a level we can scarcely imagine. Their purpose could be to act as long-term stewards of cosmic complexity, maintaining order not for centuries or millennia, but for eons. They could become the permanent caretakers of a universe that would otherwise inevitably slide into darkness and disorder. Ultimately, our human role transforms the cosmic narrative from a tragic tale of inevitable heat-death into a story of active and meaningful participation. The universe may be destined for a cold and empty end, but the intervening time, the vast stretch between now and that distant finale, is filled with potential. We have the opportunity to fill that time with meaning, with knowledge, with life, and with ever greater forms of complexity and consciousness. Our choices matter on a cosmological scale. Will we be a fleeting flash of awareness in a silent cosmos, or will we become the mechanism through which the universe consciously preserves and extends its own order? The story of emergence has, for billions of years, been written by impersonal forces. Now the pen is in our hands. We have the privilege and the responsibility to help write the next chapter. And so we arrive at the end of our journey, a story that spans from the very fabric of space-time to the inner workings of our own minds. We began in the unimaginable chaos of the Planck Epoch, a realm where the laws of physics as we know them ceased to exist, and we traced the incredible chain of events that transformed that primordial chaos into the cosmos we call home. From that formless sea of energy, the fundamental forces differentiated, creating a universe with a reliable rulebook. Quantum fluctuations, magnified by the explosive stretch of inflation, became the gravitational seeds for all structure. Matter won a tiny, crucial victory over antimatter, allowing a material universe to exist. Gravity, patient and relentless, sculpted the first galaxies and stars, whose fiery hearts then forged the heavier elements, the very stuff of planets and life. This is not merely a story of random chance, but one of deep, underlying principles. The universe possesses an inherent creative potential, a tendency to build complexity under the right conditions. Each level of organization, particles, atoms, stars, galaxies, planets, life, consciousness becomes the foundation for the next, creating a ladder of emergence. We see that the drive toward greater order is not a violation of the second law of thermodynamics, but its most beautiful expression. Every local increase in complexity, from a single cell to a swirling galaxy, is paid for by an overall increase in the universe's entropy, making us magnificent temporary eddies in a river flowing toward equilibrium. This narrative redefines our place in the cosmos. We are not just inhabitants of the universe, we are a product of its evolution, a chapter in its story. The atoms that form our bodies were forged in the hearts of long-dead stars, scattered across the galaxy by supernova explosions, and eventually assembled on a planet that orbits a stable star in the habitable zone of a spiral galaxy. After billions of years of cosmic and biological evolution, the universe has become aware of itself. Through our eyes, it observes its own grandeur. Through our minds, it contemplates its own origins. Our curiosity, our science, our art, and our search for meaning are the universe's way of understanding its own journey from chaos to order. This leaves us with a profound sense of wonder and responsibility. The fact that we can even comprehend this epic saga is a testament to the incredible order that has emerged. It invites us to see ourselves not as isolated beings on a tiny rock, but as active participants in a grand cosmic process. Our task, now that we are conscious of this story, is to become good stewards of the order we have inherited, to protect the fragile biosphere of our planet, to seek out and perhaps even spread new pockets of complexity, and to continue the fundamental human endeavor of seeking understanding. The universe began in chaos, but it has given rise to beauty, law, and consciousness. That is perhaps the most remarkable story ever told, and each of us is a living part of it.